Welcome students to the third lecture on infinite series. In the last lecture, I was talking about binomial expansions of the form 1 minus x whole to the power minus n is an integer, or 1 minus x to the power p by q, which is a rational number. In particular, we were looking at one minus x whole to the power minus half, and we have seen the coefficients of its expansion for different powers of x. Let us take a simpler problem. What is the series expansion for 1 minus x to the power half? So, this is a rational number. Let us see how to go about it. We have 1 minus x whole to the power half into 1 minus x whole to the power half is equal to 1 minus x. Therefore, if we write 1 minus x whole to the power half is equal to a 0 plus a 1 x plus a 2 x square, etc., etc., then by multiplying it with itself, we should get 1 minus x. So, let us try that. Therefore, a 0 plus a 1 x plus a 2 x square plus multiplied by a 0 plus a 1 x plus a 2 x square is equal to 1 minus x. Therefore, coefficient of x to the power 0 is equal to a 0 square is equal to 1. Again, taking the positive root, a 0 is equal to 1. Coefficient of x is equal to a 0 a 1 plus a 1 a 0 is equal to 2 a 0 a 1, which is equal to minus 1. Therefore, 2 a 1 is equal to minus 1. Therefore, a 1 is equal to minus half. Coefficient of x square is equal to a 0 a 2 plus a 1 square plus a 2 a 0 is equal to 0. Why 0? Because there is no x square in 1 minus x. Therefore, a 0 is equal to 1, we have already got. Therefore, 2 a 2 plus a 1 square is equal to 0, or 2 a 2 plus a1 is equal to minus half. So, e square is equal to 1 by 4 is equal to 0. Therefore, a2 is equal to minus 1 by 8, or we can write 1 minus x to the power half is equal to square root of 1 minus x as 1 minus half x minus 1 by 8 x square plus higher powers of x. We are going only up to the second degree of x, but if x is small, we often ignore higher powers. Okay? Example. What is consider root over 17. We can write in a similar way. We can find root over 1 plus x. Say root over 1 plus x is equal to a 0 plus a 1 x plus a 2 x square, etc. Therefore, in a similar way we can write that a 0 plus a 1 x plus a 2 x square into a 0 plus a 1 x plus a 2 x square plus is equal to 1 plus x. Now, by multiplying them and equating the powers of x, we find a 0 square is equal to 1 or a 0 is equal to 1 by taking positive value. A 0 a 1 plus a 1 a 0 is equal to 1 or 2 a 0 a 1 is equal to 1. Therefore, a 1 is equal to half. A 0 a 2 plus a 1 square plus a 0 a 2 is equal to 0 or 2 a 2 plus a 1 square is equal to 0. Therefore, 2 a 2 is equal to minus a 1 square is equal to minus 1 by 4. Therefore, a 2 is equal to minus 1 by 8. Therefore, we get square root of 1 plus x is equal to 1 plus half x minus 1 by 8 x square plus other terms which we are ignoring for the time being. Let us apply this. Find root over 17. Suppose we need to find out the square root of 17. we can write it as but if we write it like that, we are making a mistake. What is the mistake? Because this x in 1 plus x whole to the power some p, in the expansion modulus of x has to be less than 1. But if we write it like 1 plus 16 whole to the power half, then we are making a mistake. So, we write it in a different way. We write it as 16 power half into 1 plus 1 by 16 whole to the power half, right. So, that gives us a term 1 by 16 whose mod value is less than 1. Therefore, to obtain root 17, we write it as (16 to the power half) into 1 plus 1 upon 16 whole to the power half is equal to 4 into 1 plus 1 by 16 whole to the power half. And now, let us expand it using binomial. We have found out that in the expansion of 1 plus x whole to the power half, we have found out this is equal to 1 plus half x minus 1 by 8 x square plus other terms which we have ignored. Putting x is equal to 1 by 16, we get this is equal to 1 plus 1 by 32 minus 1 by 8 into 16 square. Therefore, root 17 is equal to 4 into 1 plus 1 by 32 minus 1 by 8 into 16 square. So, 4 into 1 is equal to 4, 4 into 1 upon 32 is equal to 1 upon 8 is equal to 0.125. Four into minus 1 upon 8 into 16 square is equal to minus 1 upon 2 into 16 square is equal to 2 into 256 is equal to 1 upon 512. Is equal to minus 0.0019. Therefore, square root of 17 is equal to 4.125 minus 0.0019 is equal to 4.1231. Now, if we consider root 17, I suggest all of you use your calculator to compute root 17, and you see it comes so close to 4.1231. So, this is a verification that this expansion works in a correct manner. Therefore, the final expansion is 1 plus x whole to the power p by q. We will write in a very similar way as we did with respect to negative integral index. This is equal to 1 plus p by q to the power x plus p by q into p by q minus 1 upon factorial 2 to the power x square plus p by q into p by q minus 1 into p by q minus 2 whole to the power factorial 3 to the power x cube plus. Therefore, irrespective of when we have a binomial expansion of the form 1 plus x whole to the power some index, irrespective of whether it is positive integral, negative integral or a rational, we can write it in the same way. And only thing that we have to remember that for positive integral we can write it as n choose r or NCR, that we cannot do when we have a negative integral index or a rational index like p by q, but we can rewrite it in the following form and we can get the series expansion for any binomial expression with power as an integer or a rational number. Again, this is not a proof, right? What we have done so far is not a proof. We have just verified certain results. And the assumption as I said in the very first class is Weierstrass approximation theorem. Which suggests that every continuous function in a closed interval can be approximated as can be approximated as closely as possible by a polynomial function. Therefore, what we have done, given a continuous function, we have tried to compute the coefficients of first few powers of x, and thereby we tried to find the expansion of 1 plus x whole to the power k, where k can be negative integral or rational. Let us see how to obtain the coefficients, how to obtain the coefficients. We make such an assumption that given a function f of x, it is possible to have such a polynomial expansion about a point A. So, let us write f of x is equal to a 0 plus a 1 into x minus a plus a 2 into x minus a whole square plus a 3 into x minus a whole cube, etc. The advantage of polynomial is that if it is of degree n, it can be differentiated n plus 1 times, and if we take an infinite polynomial, then we can differentiate it infinite number of times. So, with this assumption, we shall try to find out the polynomial expansion for f x. F x is equal to, we have assumed, as a 0 plus a 1 into x minus a plus a 2 into x minus a whole square plus a 3 into x minus a whole cube, etc. Therefore, f at a is equal to a 0, because all other terms will become 0. Therefore, a 0 is equal to f a. Thus, the constant term will come the functional value at a point A, about which we are expanding the polynomial. What is the first derivative of a? So, I am writing it as f upper script 1, which means I am differentiating f with respect to x once. This is equal to a 1 plus 2 a 2 into x minus a plus 3 a 3 into x minus a whole square plus 4 a 4 x minus a whole cube, like that. Therefore, what is the second derivative? Second derivative of x is 2 a 2 plus 3 into 2 a 3 into x minus a plus 4 into 3 a 4 into x minus a whole square, etc. Therefore, f 2 at a is equal to twice a 2, or a 2 is equal to f 2 at a by 2. In a similar way, the third derivative f 3 of x is equal to 3 into 2 into 1 a 3 plus 4 into 3 into 2 x minus a plus terms with higher powers of x minus a. Therefore, f 3 at a is equal to 3 factorial times a 3. Therefore, a 3 is equal to f 3 a upon 3 factorial. In a similar way, we can see that if I differentiate it once more, I will get the term f 4 at x is equal to 4 into 3 into 2 into 1 plus powers of x minus a Therefore, a 4 is equal to fourth derivative of x at a divided by factorial 4. Therefore, we can find that f of x can be written as f at a plus f prime at a into x minus a plus f second derivative of f at a into x minus a whole square upon factorial 2 plus third derivative of f at a into x minus a whole cube upon factorial 3 plus fourth derivative of a into x minus a whole to the power 4 upon factorial 4. It is not mandatory that you have to go to infinity. We can always make an approximation by expanding it to a fixed power, say k is equal to 4, and then the remaining term will be the error term in the approximation. But if the difference between x and a is very small, then as the power increases, then the error term will go to 0. So, this expansion is called Taylor series expansion of f x when f is continuous and differentiable infinite number of times at the point A. You shall study more about Taylor series in your higher classes of mathematics, but in this class we shall see how it helps us in solving certain problems. Let us consider 1 minus x whole to the power minus 2. Therefore, f x is equal to 1 minus x to the power minus 2, f first derivative of x is equal to minus 2 into 1 minus x to the power minus 3 into minus 1 is equal to 2 into 1 minus x to the power minus 3. Second derivative of x is equal to minus 3 into 2 into 1 minus x to the power minus 4 is equal to factorial 3 into 1 minus x to the power minus 4. If third derivative of x is equal to in a similar way factorial 4 into 1 minus x whole to the power minus 5. Therefore, f at 0 is equal to 1, f prime at 0 is equal to 2, f second derivative at 0 is equal to factorial 3, and if fourth derivative at 0 is equal to factorial 4. Therefore, we get f of x is equal to f at 0 plus 2 into x minus 0 plus factorial 3 into x minus 0 whole square upon factorial 2 plus factorial 4 into x minus 0 whole cube upon factorial 3. Therefore, we can write f x is equal to f at a plus f first derivative at a into x minus a plus f second derivative at a into x minus a whole square upon factorial 2 plus f third derivative at a in x minus a whole cube upon factorial 3 plus f fourth derivative of a into x minus a whole to the power 4 upon factorial 4 like that, and putting the values f of x is equal to 1 minus x whole to the power minus 2 is equal to f at 0 plus f prime at 0 into x plus f second derivative at 0 into x square upon factorial 2 plus third derivative of f at 0 into x cube upon factorial 3 plus fourth derivative of f at 0 into x 4 upon factorial 4 is equal to f 0 is plus 2 times x plus factorial 3 into x minus 0 whole square upon factorial 2 plus factorial 4 into x minus 0 whole cube upon factorial 3 etc. is equal to 1 plus 2x plus 3x square plus 4x cube plus, and these are the terms that we have already seen, right. We have already seen that 1 minus x whole to the power minus 2 is equal to 1 plus 2x plus 3x square plus 4x cube, like that. So, Taylor series expansion works for 1 minus x whole to the power minus 2. I want you to verify the same with other polynomial expansions that we have done already in this class, and I shall go beyond polynomials. If I ask you what are the other functions that you can remember very easily, which is differentiable smoothly for different values of x, the first one that comes to my mind is the trigonometric functions. In particular, let us look at sin x, cos x, tan x, right. Let us see whether we can expand this using Taylor series expansion and find a way to compute sin of x or cos of x or tan of x, etc. Because if you remember, in classes we see the values of sin x, cos x, etc. are only for a fixed set of values, right. We have seen for 0 degree, for pi by 6, for pi by 4, pi by 3, pi by 2 and pi, and typically we work with their multiples, or perhaps with some more trigonometric manipulations we can get for 15 degrees, 18 degrees, etc. right. What if I ask you what is the sine of 1 degree, or what is the sine of 5 degrees? It is not easy to compute those values unless we use a Taylor series expansion. That is why this formula is very, very important for analysis. So, for illustration, consider sin x. F x is equal to sin x. Therefore, f 0 is equal to 0. First derivative of x is equal to cos x. Therefore, first derivative at 0 is equal to cos 0, which is equal to 1. Second derivative of x is equal to minus sin x. Therefore, second derivative at 0 is equal to 0. Third derivative of x is equal to minus cos x. Therefore, third derivative at 0 is equal to minus 1. I will go for a few more. The fourth derivative of x is equal to sin x. Therefore, fourth derivative at 0 is equal to 0. Fifth derivative of x is equal to cos x. Therefore, fifth derivative at 0 is equal to 1. So, let us stop here, and we know that from Taylor's theorem, from Taylor's series, f of x is equal to f of 0 plus f prime at 0 into x minus 0 plus f second derivative at 0 into x minus a whole square upon factorial 2, etc. Therefore, from Taylor's series, f of x is equal to f at 0 plus f prime at 0 into x minus 0 plus f second derivative at 0 into x minus a whole square upon factorial 2 plus third derivative at 0 into x minus a whole cube upon factorial 3 plus fourth derivative of 0 into x minus a whole to the power 4 upon factorial 4 plus a fifth derivative of 0 into x minus a whole 5 upon factorial 5 plus like that we will go. I am not going any further. Let us replace the values. F 0 is equal to 0, f first derivative at 0 is equal to 1, f second derivative at 0 is equal to 0, f third derivative at 0 is equal to minus 1, f fourth derivative at 0 is equal to 0, and f fifth derivative at 0 is equal to plus 1. This is what we have got. Putting these values, we get sin of x is equal to sin at 0 plus 1 times x minus 0 plus 0 times x minus 0 whole square upon factorial 2 minus 1 times x minus 0 whole cube upon factorial 3 plus 0 times x minus 0 whole to the power 4 upon factorial 4 plus 1 times x minus 0 whole 5 upon factorial 5. Like that, this is equal to 1 times x minus x cube upon factorial 3 plus x to the power 5 upon factorial 5. If we continue further, we shall see that this is equal to x minus x cube upon factorial 3 plus x to the power 5 upon factorial 5 minus x to the power 7 upon factorial 7, like that. That is, we shall get a polynomial where only odd powers of x are there, and the coefficient for x to the power k is 1 upon factorial k, and the signs of them are going to be plus minus in an alternative way. Similarly, we can work out for cos x, and I like you to verify that cos x is equal to 1 minus x square upon factorial 2 plus x to the power 4 upon factorial 4 minus x to the power 6 upon factorial 6, like that. That is, when we look at cos x, we find only even powers of x, and again like sin, we get alternatively positive and negative signs. Next, we look at tan x. Again, we expand about 0. F 0 is equal to tan 0 is equal to 0. F 1 at x is equal to d dx of tan x is equal to sec square x is equal to 1 plus tan square x. Therefore, f 1 at 0 is equal to 1. What about f 2 x? That is second derivative of x is equal to d dx of 1 plus tan square x is equal to two tan x into sec square x is equal to 2 tan x into 1 plus tan square x is equal to 2 tan x plus 2 tan cube x, right. Therefore, f 2 at 0 is again 0, but we needed this expansion so that we can go to the third derivative. Therefore, f 3 x is equal to 2 into 1 plus tan square x plus 6 tan square x into 1 plus tan square x is equal to 2 plus 2 tan square x plus 6 tan square x plus 6 tan 4 x. Therefore, f 3 at 0 is equal to 2. F 4 x is equal to d dx of this because derivative of the constant is 0. Therefore, x 4 x is equal to d df of 8 tan square x plus 6 tan to the power 4 x is equal to 16 tan x plus 16 tan cube x plus 24 tan cube x into 1 plus tan square x. Therefore, f 4 at 0 is equal to 0. In a similar way, we can get f 5 x is equal to 16 into 1 plus tan square x plus terms with tan x. Therefore, f 5 at 0 is equal to 16. Therefore, by expanding up to this point, we can get that tan x is equal to 0 plus 1 upon 1 factorial x plus 0 times x square upon factorial 2 plus 2 times x cube upon factorial 3 plus 0 times x 4 upon factorial 4 plus 16 times x to the power 5 upon factorial 5 plus higher powers of x. On simplification, we get tan of x is equal to 0 plus x plus 0 times x square plus 2 into x cube upon factorial 3 plus 0 times x to the power 4 plus 16 times x to the power 5 upon factorial 5. Now, this is equal to x plus x cube upon 3 plus 16 upon factorial 5 is equal to 120. So, this is 4 upon 30 is equal to 2 upon 15 is equal to 2 upon 15 times x to the power 5 plus higher powers of . Thus, we get an approximation of tan x in the form of a polynomial up to 5th power of x. Okay, students, I stop here today. In the next class, I will look at some more problems. In particular, I will look at how to obtain the Taylor series expansion for tan inverse x, for logarithmic functions, in particular log of 1 plus x, and more importantly the expansion of e to the power x, which is very important in analysis. Okay.